In this video, we're continuing to investigate some general properties of Laplace transforms that are useful in connection with their application to differential equations and other applications of Laplace transforms. In the next example, example 5, we're going to be able to use either number 3 in my table or number 4 in my table. We could do this one either way to get the solution. It's fairly easy to get the answer either way, and it's kind of, I hope, a fun and interesting example. So to give us some additional practice with those properties and see how everything fits together. So if I think of that function in terms of number 3, the shift property, that means I'm thinking of it as being e to the 3t times the known function t squared. We know the Laplace transform of that is 2 over s cubed. We investigated that in the previous video. So from the shift property, we can just take that function, the transform of t squared, and shift it by 3, since we're multiplying by e to the 3t in the time domain. And if we do that, we just end up with 2 over s minus 3 cubed using the shift property as our answer for the transform of the function t squared e to the 3t. We could also find the transform of that function using property number 4, which we learned in the previous video, where when we do it that way, we're thinking of f of t as e to the 3t as being our known function, which has s minus 3 to the minus 1 as its transform. And then using property number 4, we think of that as being t squared times our known function. So with that approach, we need our first derivative and our second derivative of that function of s. And then using property number 4 and plugging in, minus 1 squared is just 1. And so our answer, again, is 2 over s minus 3 cubed, which agrees with the answer that we got doing it the other way. You probably will find it easier in a problem like this where you have the option of using either number 3 or number 4. It's probably going to be easier to think of it in terms of property number 3, because all you're doing is a shift and you don't have to calculate any derivatives. So the first way we did it's probably less work, but it's kind of fun to see that you end up getting the same thing either way. Now the red line here in this video, we're still in section 3.2, learning some general properties of Laplace transforms. The next topic doesn't necessarily have a lot to do with the material that we looked at previously here in this video and in the previous video. But we're going to define a function that you may or may not have seen before called the unit step function. And then we'll look at its transform and we'll look at a few applications. We're only going to do a little bit with this right now. This is actually one of the reasons why, one of the advantages of Laplace transforms in connection with differential equations and other subjects, because using Laplace transforms you can easily handle functions like this one that are hard to manage using more standard techniques for differential equations that we learned earlier in the course. And people in electrical engineering and control systems, signal processing, a lot of times deal with functions like this and more complicated things. And Laplace transforms are a really good tool for analyzing things like this. So that's why we're looking at this type of function here. So here's a definition of the unit step function, the formula for it. And that formula, I hope, becomes a little more transparent if we look at this graph over here. So the unit step function has the value 0 up to a certain time, t equals c, at which time we're thinking of it as being a unit signal or unit voltage or something like that that's being switched on at time t equals c, and then it has the unit value 1 thereafter. So that's basically the definition. That's the physical interpretation of it here in terms of engineering applications in the graph up here. And so the first thing we want to do is start looking at Laplace transforms in connection with this function. And this is sometimes called the second shift theorem. This is property number 9 in my table. When we have a shift in the time domain, what happens? It turns out we get a kind of multiplication by an exponential in the Laplace transform domain. So remember, with the first shift property, we were multiplying by an exponential in the time domain, and we ended up having a shift in the Laplace transform domain. Here we have a shift in the time domain, and we end up getting a multiplication by an exponential in the Laplace transform domain. Again, the proof is not too difficult, just using the definitions, so I think it's worth looking at the proof here. Just like with all the other proofs we look at, we start out just by plugging in the function that we're transforming into our definition. That's what's happening here. Because u to the t minus c is 0 until t is c or greater, that has the effect of cutting off the first part of this integral, the part from 0 to c, where your integrand is 0. And so you just end up integrating from c to infinity of that thing. And on that interval, u of t minus c is 1. So that simplifies the form of the thing we're integrating a little bit. Then we're going to make this substitution. We're going to let x be t minus c to get this thing into the form that we want. Then dx will be dt, and t will be x plus c. And we're going to change over the limits of integration also in the next step. So when t is c, the corresponding x limit is 0. If we go back and look at our change of variable when t is c, x is equal to 0. So that's going to be the lower limit in our integral when we change it over to x. And we're thinking of c as being some finite value, so when t is infinity, x is going to be infinity. So that gives us this for our integral for the Laplace transform, where now x is our integration variable. And if we break up the exponential, we'll have e to the minus sx and e to the minus sc, and e to the minus sc we can pull out from the integral because that doesn't involve x, so that's just constant as far as the x integration is concerned. So that's what's happening here. And then this thing that we're left with is basically just the Laplace transform, the definition of the Laplace transform, except with x as the integration variable instead of t. So that integral is just the Laplace transform of f, and so we end up with that exponential times f of s as the Laplace transform of the function that we started with. So that proves property 9 in the table, the second shift theorem. Number 8 in the table then gives us the transform of just a unit step function by itself without anything else going on. If we just take f of t to be 1 in the formula that we just proved on the previous slide, then big F of s will be 1 over s, and we immediately get formula number 8 for the Laplace transform of any unit step function. And we'll wrap this up now with kind of an application, a combination of unit step functions. So let's say for starters I give you this graph, and then I might ask you to take a graph something like that and then express it in terms of unit step functions. So that's the first thing we need to do, and here I'm trying to explain how we can picture this graph in terms of this combination of 3 unit step functions here. So the idea is we start out with a signal of strength 1 at the beginning. If we take the unit step function, which has signal strength 1, multiply it by 5, we have a signal of strength 5 at the beginning. And once that signal of strength 5 is turned on, it stays on. And that's our function up until we get to time t equals 7. At that point, we want to turn on an additional 1. So our 5 is, remember, stays on. So when 5 stays on and we turn on an additional 1, that will give us our jump up to 6, which we see happening in our graph here. So that takes care of the first 2 pieces in our graph. And then both of those signals, once they're turned on, stay on forever. So if we don't do anything else, we would just have the constant value 6 from then on. But we wanted, based on our graph, we want to drop back down to 4 when t is equal to 13. So we add one more piece here. And without that piece, we've still got 6 going on forever. So we want to drop it down to a value of 4. So we take minus 2 times the unit step function turned on at 13. And then 6 minus 2 is 4. Gets us the signal that we want then, and it just maintains that constant value then forever. So that's how we can deal with that type of function that I circled by expressing it in terms of as a linear combination of 3 unit step functions. Once we have that, we can just use linearity with the property up above. So Laplace transform of 5 u of t is 5 over s. Laplace transform of u of t minus 7 is e to the minus 7s over s. And again, we're using linearity, or in other words, Laplace transforming term by term, minus 2 e to the minus 13s over s. So we have a common factor in each of those terms of 1 over s, which we can pull out if we feel like it. So that would be the Laplace transform of that crazy function in the graph. You'll probably want to study the examples in the book along with the examples in this video to get more comfortable with these properties. And there is a handout in your packet, something like Find the Laplace Transform, with a whole lot of other examples you can try for additional practice to get more comfortable with applying these properties. You'll want to definitely keep your Laplace transform table handy from now on.